So in section 4, we're going to look at a difference in mean. So we're going to talk about the confidence interval for a difference in mean, and then also performing a significance test for a difference in means. So to start off, I kind of want to review what we discussed in chapter 5. So remember when we were doing a difference in means for sampling distribution, we had two populations or treatments, each with their own population mean and standard deviation mean, and with their own statistics, so their own sample mean and sample standard deviation. And then they each had their own sample size, N1 and N2. So it's just kind of reviewing when we discussed this in chapter 5. So when it comes to the sampling distribution for a difference in two means, the shape is approximately normal under one of two conditions. Either if the population distributions are normal, then we can say the combined sampling distribution is approximately normal, which means if your populations are normal, their difference will be normal as well. If we do not know that the sampling distribution for their difference will be normal, then we have to make sure both sample sizes are large enough. So that means that N1 has to be greater than or equal to 30, and N2 has to be greater than or equal to 30. Then our center is calculated by just subtracting our population means, as long as we are taking a random sample or we have random assignment. And then our spread, our standard deviation, was calculated by doing the square root of our population standard deviation over N1 squared, and then the second population standard deviation squared over N2. And that was as long as we had independence. So our sample sizes both had to be less than or equal to 10% of their populations. So the first thing we're going to talk about is a two-sample Z statistic. So as long as you are doing a Z statistic, that means you know the population standard deviation, then we can use the standard deviation formula that we did in chapter 5. We can use the square root of standard deviation 1 squared over N1 plus standard deviation 2 squared over N2, all underneath the square root. Then as long as, obviously it's normal and also random, and you've checked for independence, the formula to calculate our test statistic is then done by Z equals, and then we'll have x1 bar minus x2 bar minus mu1 minus mu2. Now, often this will most likely be 0. Because again, when we do a significance test, our null hypothesis is that their difference is 0. So most of the time, mu1 minus mu2 is going to be 0. And then over our standard deviation formula, now obviously if we don't know our population standard deviation, the formula changes slightly and we use our sample standard deviation instead. So that becomes the square root of S1 squared over N1 plus S2 squared over N2. So again, similar to when we were conducting just a regular confidence interval for a mean, if we didn't know our population standard deviation, we used our sample, which became standard error. And it becomes the estimated standard deviation. Now, if we have to do this, we are obviously no longer going to be having a z statistic. We will now have a t statistic. So this changes the formula. So instead of it being z equal, it would be t equal. And our numerator doesn't change. It's still x1 bar minus x2 bar minus mu1 minus mu2, which again will most likely be 0. It's not always going to be 0, but majority of the time. All over the square root of s1 squared over n1 plus s2 squared over n2. Now, obviously, if we're using a t statistic, we need our degrees of freedom. And degrees of freedom does not work the same way it did when we were talking about it previously in Chapter 7. There is a formula that is used to calculate degrees of freedom that is a lot more complicated than just sample size minus 1. And that's because we now have 2 sample sizes instead of 1. So option 1 is to use the actual formula, which we are not going to do. For a couple reasons. One, it's a very time-consuming and complicated formula. And also, you very rarely, if ever, will get a degrees of freedom as a whole number. Now, when we talk about how to do this in the run the confidence interval and significance tests in your calculator, it will give you the degrees of freedom using this formula. So your degrees of freedom will be a decimal if you use the calculator. But we're not going to go with option 1. We're going to go with option 2, which is much, much nicer of an option. And what we end up doing is whichever sample size is smaller, we use its degrees of freedom. So whatever is smaller between n1 minus 1 and n2 minus 1, that's the degrees of freedom we'll use. And it's considered a conservative method. But it's a lot easier for us to do. So just kind of review our conditions for calculating a confidence interval or performing a significance test did not change from Chapter 5 when we were doing sampling distributions for difference in means. You do have to have random. Either both samples have to be random or you have to have a random assignment to your 2 groups if you're doing an experiment. For independence, you have to check the 10% condition for both samples. And if an experiment, it's not needed. You just need to check to make sure that each trial is independent. And then lastly, your normal. So either both populations have to be normally distributed, in which case they're differences. Either that or both sample sizes are large enough, greater than or equal to 30. Now, if neither of those conditions are met and you have your data, you need to check the graph to make sure it is approximately normal. So let's talk about the 2-sample t interval for a difference between 2 means. So if you're going to try to find the confidence interval based on a sample standard deviation, then we do x1 bar minus x2 bar plus or minus our t critical value times our standard deviation, which is s1 squared over n1 plus s2 squared over n2. And we calculate our critical value t the exact same way we did when we're doing a single confidence interval. You use INVT and you use your degrees of freedom, which is the smaller of n1 minus 1 and n2 minus 2. And I will show you how to do this in the calculator as well as by hand when it comes to actually calculating the confidence interval. Then if you're talking about a significance test, as long as your conditions are met, and like I said, your null hypothesis is almost always going to be mu1 minus mu2 equals 0, then our test statistic t equals x1 bar minus x2 bar minus mu1 minus mu2, which I've already stated multiple times, most likely going to be 0, all over the square root of s1 squared over n1 plus s2 squared over n2. And again, we'll find our p-value the exact same way we did when we were performing a significance test in the previous section. And again, we'll use our alternative hypothesis, whichever way it's stated, and using our degrees of freedom the same way for a confidence interval. So a couple different ways you can see your alternative hypothesis. So you can write mu1 minus mu2 is greater than 0, or you can write it as mu1 is greater than mu2. It means the exact same thing. For the alternative, their difference not equaling 0. Another way to say that is that they are not equal to each other. And then lastly, if their difference is less than 0, that's the same way as saying mu1 is less than mu2. You could see either of these written for your alternative hypothesis, so it is important you know how to convert that back to their difference being greater than, less than, or not equal to 0. So here's how we're going to do this on the calculator. So if you need to do a 2-sample t interval, you're going to go to, for both of these, stat and then tests. And the 2-sample t interval is going to be number 0. So you're going to look for number 0. And then again, just like when we're doing a regular confidence interval, you can input data. So if you have data listed into list 1 or list 2, or you can use stats, which is going to be very common. So if you have to input stats, you need to know your x1 bar, your sample standard deviation for your first one, and your n1. Then you need to know the same thing for x2. And then you need to know your confidence level as a decimal. And when it says pooled, we are always going to pick no. Okay? We are never going to pool our means. We do it for proportions, but we don't do it for means. And then for a 2-sample t-test, you again go to stat and then tests. And the 2-sample t-test is number 4. So again, you have the option of entering data or stats. So data is a lot easier because then you just have to pick your alternative hypothesis. But if you're doing stats, you need to know a lot of the same information. You have to know x1 bar, sx1, and n1. You need to know x2 bar, sx2, and n2. And then you have to choose your alternative hypothesis. Either it does not equal, is less than, or is greater than. And again, when it says pooled, you're going to choose no. So let's go ahead and do some examples. We have that observational studies suggest that moderate use of alcohol by adults reduces heart attacks and that red wine may have special benefits. One reason may be that red wine contains polyphenols, substances that do good things to cholesterol in the blood, and so may reduce the risk of heart attacks. In an experiment, healthy men were assigned at random to drink half a bottle of either red or white wine each day for 2 weeks. The level of polyphenols in their blood was measured before and after the 2-week period. Here are the percent changes in level for the subjects in both groups. Dot plots of both distributions show no outliers or strong skewness. Construct and interpret a 90% confidence interval for the difference in mean percentage changes in polyphenol levels for the red wine and white wine treatments. Does the interval suggest that red wine is more effective? Explain. So first we have to pick what x1 and x2 are going to be. So we're going to have x1 be our red wine levels and x2 be the white wine levels. Now we're going to check our conditions. So for random, this was an experiment. So we do have that there was random assignment to the 2 treatment groups. Okay. And then because it is an experiment, for independence, we can say that each trial is independent, which means that one man's consumption levels did not affect another. And then for normal, we don't have the necessary sample size because our sample size is only 9. It doesn't say anything about the population being normal, but it does say that dot plots of both distributions have no outliers or skewness, which is just another way of saying that they're normal. So now that all of my conditions are met, I can go ahead and start calculating my confidence interval. So the first thing I need to do is calculate my mean and standard deviation. So to do that, I'm going to go into Stat and then Edit, and I'm going to put my levels into List 1 and List 2. So my red wine is going to be List 1, my white wine is going to be List 2, because that corresponds with what X1 and X2 are. And then I'm also doing this because I'm going to use the calculator data feature to show you how to do the confidence interval later. So I want to make sure that I already have it in my calculator. And it is okay here for the levels to be negative. So what that means is their percent change, instead of it increasing, it decreased. So it's okay for our values to have negatives here. So when I go to Calc, then after I have my data in, I'm going to go to Calc, and then I'm going to go to Variable Stats, and I'm going to write down my information. So X1 bar is 5.5 with a sample standard deviation of 2.52. And X2 bar, which they'll label as Y hat, is 0.233 with a sample standard deviation of 3.29. Now obviously we did have to round here for not the X bar for our first one, because that's exactly 5.5, but we did have to round our other mean and both of our standard deviations, which is where using the calculator here is going to be a little bit more beneficial when calculating our confidence interval. Now I need to find my T critical value. So we have we're going to go to second bars, and we're going to go to INVT. And for our area, because we want to be 90% confident, we take our remaining percent 10, divide by 2, so our area is 0.05. And then for our degrees of freedom, both of our sample sizes are the same. They're both 9. So 9 minus 1 is 8, so my degrees of freedom are going to be 8 in this case. And we're going to get a T critical value of 1.86. Now I'm going to calculate the confidence interval. So I'm going to start with subtracting x1 minus x2, so 5.5 minus 0.233, plus or minus my critical value, 1.86, times the square root of 2.52 squared over 9 plus 3.29 squared over 9. So 5.5 minus 0.233 is going to give us 5.267 plus or minus 1.86 times our standard deviation formula. It's going to give us 2.569. So we're going to add and subtract that from our mean of 5.267, and we're going to get 2.698 when we subtract, and 7.836 when we add. So before I show you how to do it in the calculator, I'm going to go ahead and write my sentence. So for our conclusion, we can say we are 90% confident that the true mean difference in polyphenol levels, where we did red minus white, is between 2.698 and 7.836. So that's the first part where we construct our interval. And the second part is, does the interval suggest that red wine is more effective? So when you're trying to make that conclusion, it's whether or not the difference contains all positive numbers. Because in that case, that would tell us that red wine is more effective. If the interval contained even one negative number, then we couldn't say for sure that it is more effective. Now, obviously, if all of the numbers were negative, it's definitely not. So for us, so the interval suggests red wine is more effective because it contains only positive values. So now I'm going to show you how to do this on the calculator. So we go to stat and we go to tests, and then we go all the way down to 0. And this time for our input, we're going to choose data, because we have it listed into list 1 and list 2. So our list 1 is L1, our list 2 is L2, our sea level is 0.9, pooled is no, and then you hit calculate. And we're going to get 2.845 to 7.689. So definitely more accurate of a confidence interval here. I would accept either one on an assignment or an assessment, as long as you are telling me, either showing all of the work for doing it by hand or telling me what you input into the calculator. No matter which method you choose, you still have to set up the confidence interval. I still need this statement right here that shows me you understand how the confidence interval is calculated, what formula is used. Even if you don't then do the math based on that, but you use the calculator to finish calculating your interval. So our second example says, does increasing the amount of calcium in our diet reduce blood pressure? Examination of a large sample of people revealed a relationship between calcium intake and blood pressure. The relationship was strongest for Black men. Such observational studies do not establish causation. Researchers therefore designed a randomized comparative experiment. The subjects were 21 healthy Black men who volunteered to take part in the experiment. They were randomly assigned to 2 groups. 10 of the men received a calcium supplement for 12 weeks, while the control group of 11 men received a placebo pill that looked identical. The experiment was double-blind. The response variable is the decrease in systolic, which is the top number of your blood pressure, for a subject after 12 weeks in millimeters of mercury. An increase appears as a negative number, and we have our data. So for the group 1 that was taking the calcium and the group 2 that was taking our placebo. Do the data provide convincing evidence that a calcium supplement reduces blood pressure more than a placebo? Carry out an appropriate test to support your answer, then interpret up the p-value you got in the context of this experiment. So first thing we want to do is identify our X1 and our X2. So I'm going to have X1 be my group 1 and X2 be my group 2. So for my null hypothesis, it would be that there is no change between the two groups. So mu1 minus mu2 equals 0. For the alternative hypothesis, we want to know, does taking calcium reduce blood pressure? Which means we would have that mu1 minus mu2 is greater than 0. Because as they stated, an increase appears as a negative number. So a decrease would be positive. So their difference would be greater than 0. Now we want to check our conditions. So for random, this was an experiment, and it does say that there was random assignment between the two groups. For independence, again, this is an experiment, so each trial is independent. And then lastly, normal. So unfortunately for us, our sample sizes are 10 and 11, not greater than or equal to 30. We're also not given that the population distribution is normal, which leaves us for checking for our graph. So there's a couple ways you can do this. You can create a dot plot if you like. You can create a histogram. But in either case, when you do your graph, you're going to see that both graphs are approximately normal. So now we met all of our conditions, we want to go ahead and calculate our mean and standard deviation. So very similar to the previous example, I'm going to go ahead and put my data into the list feature in my calculator. So list 1 will be my group 1, which is the calcium. And then list 2 will be the placebo group. That had the identical pill. Now, unlike the previous example where I could go to 2 variable stats, I can't do that here because my sample sizes are not the same. So I'm going to have to calculate my distributions twice. So the mean of my first group is 5 with a sample standard deviation of 8.74 and a sample size of 10. When I calculate it for my second group, we have a sample mean of negative 0.273 with a sample standard deviation of 5.9, and our sample size is 11. Very similarly to our previous example, the only value here that is exact is our X1 mean. All the other ones are rounded. So again, using our calculator, probably a better option to find our p-value than using the formula. But you still have to show me the formula steps. So for our formula, we would do x1 minus x2, so 5 minus negative 0.273. And I don't have to subtract 0 from that. All over the square root of 8.74 squared over 10 plus 5.9 squared over 11, which is going to give us a test statistic of 1.6. So now you can do TCDF, and because we're looking for the difference between greater than 0, our lower bound would be 1.6, the upper bound would be the 1E99, and for my degrees of freedom, I use the smaller group's degrees of freedom, which means my degrees of freedom here would be 9. And that is going to give us a p-value of 0.072. Now, it does not give us a level of significance alpha. And whenever we are not given a level of significance, we always use 0.05. So when I compare that to 0.05, it is greater than 0.05, which tells me we are going to fail to reject our null hypothesis. So for our sentence, we say there is not enough evidence to show a calcium supplement reduces blood pressure more than a placebo. So that was the first part of the question. And then the second part was to interpret your p-value, what it means. So what that means is, so if I'm interpreting my p-value, that tells me if calcium has no effect because it is based on your alternative hypothesis, your null hypothesis, and then we, on blood pressure, then we would say 7.2%, because we can convert it to a percent, of studies will obtain this result or more, because it's always in the direction of your alternative hypothesis, which in this case is greater than, because of random error. So when you're interpreting p-value, it's always based on your null hypothesis being true. You convert your p-value to a percentage, and then you do that in context of your alternative hypothesis, and then it's always because of random error. So the last thing I want to talk about before we do the last part is the p-value using the calculator. So we go to stat and then tests, and then we want our two-sample t-test, which is number 4. We would use data. List 1 is L1, list 2 is L2, and then we use mu1 is greater than mu2, pooled no, and then you hit calculate. So our p-value is slightly different when we use that part of the calculator. We're actually going to get 0.064 as our p-value, which is more accurate here, again, because it actually uses the correct calculated degrees of freedom, and it didn't round the means or the standard deviations or even as much as we did. So I would accept either p-value. They both result in the same conclusion. Like I've said previously, using the calculator versus the test on the calculator versus just TCDF should not change the results for your answer. So the last thing we're going to do is kind of talk about the relationship between confidence intervals and significance tests. And we're going to do that by looking at an example. So it says researchers are interested in whether or not women who are part of a prenatal care program give birth to babies with a higher average birth weight than those who do not take part in the program. A random sample of hospital records indicates that the average birth weight for 75 babies born to mothers enrolled in a prenatal care program was 3,100 grams with a standard deviation of 420 grams. A separate random sample of hospital records indicates that the average birth weight for 75 babies born to women who did not take part in a prenatal care program was 2,750 grams with a standard deviation of 425 grams. We know, do these data provide convincing evidence that mothers who participate in a prenatal care program have babies with a higher average birth weight than those who don't? And we're going to assume all of our conditions have been met, and we're going to use our calculator to answer the questions. So the first thing we want to do is construct a 99% confidence interval to estimate the true mean difference in mothers who participate in a prenatal care program and those who don't. And I'm just going to use the test on the calculator. I'm not going to do it by hand. So X1 is going to be, let's go ahead, and X1 is going to be the mothers who do participate. And X2 is going to be do not participate. So X1 bar is 3,100, X1 is 420, and N1 is 75. X2 bar is going to be 2,750, X2 is going to be 425, with the same sample size of 75. So when we do the test in the calculator, we're going to go to 0 for our 2-sample T interval. We're going to do stats, and we're going to input this information for stats. Change our C level to 0.99 because it is automatically 0.90 in the calculator. And when we calculate, we get 169.96 to 530.04. We now will talk about that more in a little bit. We're now going to conduct a significance test to determine if there is a significant difference in mothers who participate in a prenatal care program and those who don't. And we're going to use a 1% significance level. So in this case, our null hypothesis would be that mu1 minus mu2 is 0, that there isn't one. Our alternative hypothesis is not asking us to see specifically that the care program is better. It just wants to know, is there a difference? So our alternative hypothesis is going to be that mu1 minus mu2 does not equal 0. Anytime it says conduct a significance test to determine if there is a significant difference, that's an alternative hypothesis of does not equal. So again, we'll go ahead and use the test on our calculator. So we go to stat, test, and then number 4. We're going to input the exact same stats that we used for our confidence interval, and our alternative hypothesis will be does not equal. Then we hit calculate. So we get a test statistic of 5.07, and our p-value, if you look, is going to be in scientific notation. It's 1.157 and then e negative 6. So remember, 1 less 0, so that means 5 zeros, and then 116. Now, obviously, this is going to be less than our level of significance of 1%, which means we would reject our null hypothesis, which means we would say that there is evidence to show a significant difference. So that leads us to the third part. What type of results did you get? So because our interval did not contain 0, we would say that there is a significant difference. So anytime you're trying to compare make a conclusion about something with a confidence interval without running the significance test, we'll talk about this more. It only works if you're looking for a significant difference though, where you're all, which is a does not equal. You look to see whether or not your interval contains 0. And that could mean that all of the values are positive or all of the values are negative. We're not specifically saying in which direction. We're just saying that there is a significant difference. So because 0 is not contained in our interval, there is a significant difference. And then for our significance test, our p-value was less than alpha, which means there is also a significant difference. So what that tells me is if you do a confidence interval and a significance test they should give you the same results. Now, there are a couple kind of things that go along with this. And it only works in a two-sided test, which means the alternative hypothesis does not equal. So you have to have a significance level of alpha and a confidence of whatever 1 minus that is. So if my significance level is 1%, my confidence interval has to be 99% because those add to 100. So if my significance level was 0.05, my confidence interval has to be 95%. So if your significance test rejects your null hypothesis, then the confidence interval will not contain your mean of 0. And if you fail to reject, then the confidence interval will contain it, which means the confidence interval will contain 0. So it's kind of a nice thing. It only works for two-sided though, where you're comparing them. So you can use a confidence interval to make an inference about the population instead of performing a significance test. So let me know if you have any questions about making inferences for a difference in means, whether or not that's a confidence interval or a significance test. All of the examples we did do in the notes were based on performing a t-test statistic, since that's going to be the most common one we do. However, there may be cases where you have to do a z-test statistic, in which case all that means is instead of using a t statistic, you would use z. So it works very, very similarly, and you would just use 2-sample z-int in the calculator and 2-sample z-test in the calculator. Other than that, it's the exact same thing.